Hi guys, welcome to Science in 5. In this video we're going to discuss the trial exam for physics paper 1 2021. Right now we're moving on to section B now. We are going into the mechanics section. In the previous video we looked at multiple choice questions. Again, a physics paper is a calculation based paper, guys, so you need to practice calculations. Don't fall into the trap that says, I don't need to learn my formulas, they'll be in the formula sheet. That will not really help you with developing a skill for calculation. I always encourage learners to read the whole question and then, from there, after you've read the whole question, make sense of everything. So this paragraph of information is so critical to make sense of the whole question. Two blocks of mass 4 kg are connected by means of a light and extensible string P. The system is pulled up by a constant force of 50 newtons up a rough inclined plane that is set 30 degrees to the horizontal. The system accelerates up the incline at 0.25 meters per square second. The friction that acts on the block of mass m is 3 newtons. The coefficient of kinetic friction that acts on the 4 kg block is 0.24. Now, there's a handful of information there, guys. So part of passing physics papers is learning how to extract information. Let's read the whole set of questions, then we answer. 2.1, state Newton's second law in words. 2.2, draw a free body diagram showing all the forces that act on the 4 kg block. 2.3, calculate the following: the magnitude of the tension in the string. And 2.3.2, the value of m. 2.4 says a hypothetical planet Red Pack has a mass that is double that of the Earth and its radius is 3 times that of the Earth. Calculate the weight of an astronaut of mass 75 kilograms that lands on the surface of Red Pack. Okay, so now I'm going to switch to my board and let's get moving with this question.
It says state Newton's second law in words. Now at this stage there are two versions of Newton's second law that we can discuss. The first one says F net is equal to MA. So according to this version, when you're writing it out in words, you'd say when a net force acts on an object of mass m, it will cause the object to accelerate in the direction of the net force with an acceleration that is the magnitude of A, right? The acceleration is directly proportional to the net force and is inversely proportional to the mass. So based on this law, we get these two ideas. Acceleration is directly proportional to net force. Acceleration is inversely proportional to mass. So that's one idea. Probably we learned this in grade 11. The other idea says, well, the net force is equal to the rate of change of momentum. So the top part is delta P, the bottom part is delta T. We call this quantity the rate of change of momentum. So we can use either one of those definitions. We can say the net force is equal to the rate of change of momentum, or we can define the net force in terms of the acceleration. Straightforward. Now 2.2 says draw a free body diagram showing all the forces that act on the 4 kg block. So there's my 4 kg block. So sometime I feel like I'm gonna run out of space so soon, right? So I'm trying to see whether I can fit 2.2 here and then continue there. Maybe it'll make sense if I fit 2.2 here, then I create space. Okay, 2.2, a free body diagram for the 4 kg block. So the moment you draw a free body diagram for inclined plane motion, I always say to learners, it's best to mimic the inclined plane. It's inclined like this. So imagine I'm drawing a tilted Cartesian plane. This will be my normal x. Perpendicular to the x will be the y. Y. Now, if you draw all the forces that act perpendicular to on that 4 kg block. It will make the calculation easy. You might choose to draw the gravitational force going down, not a problem, but it always helps to draw the forces that act perpendicular. You'll see why. Okay, so the first force that we can see that's acting on the 4 kg block, what causes the 4 kg block to move up? Tension. So there's a force of tension in the rope, pulls the 4 kg block up. What force opposes the motion of any object? Goes in the opposite direction. Frictional force. What other force pulls the block down? Well, we know generally the force of gravity always acts downwards. Gravitational force always acts vertically downwards. Right? But in this case, the block slides down the incline. So there's a component of gravity that acts down that slope. We call this component what? FG parallel. Or you can use W parallel. It's fine. And then, now let's draw the perpendicular forces. The first force we can think of that is always perpendicular to any surface is the normal force. And the force that balances out the normal force is this component of gravity, which we call FG perpendicular. Draw a free body diagram like this, always. Or if you don't want to draw it like this, you want to draw the FG instead, it's fine, but as long as you can see the perpendicular forces. The advantage of this free body diagram is you'll see, when we want to calculate determine forces which affect motion, it's only these forces parallel to the slope. These two, we leave them out. When we want to calculate the normal force, we look at the forces that are acting perpendicularly. These are parallel forces, we leave them out. Okay, so that's how I would draw that diagram. Notice in the question it says 4 marks. So which means there are 4 forces here. Generally, one force, there's the second force, there's my third force. Now, these two are going to be regarded as one force, the 2 components, because they are coming from this gravitational force. So that's those are the 4, they make up the 4th force. So that's how I get my 4 marks. Okay. All right. Now, the next question says calculate the following. Now I'm doing a calculation. I need the magnitude of the tension in the string. I need this force here. The magnitude in the tension in string P. I've just been asked to draw a free body diagram. Now I'm performing a calculation. So it's a pattern. When you see a question that says draw a free body diagram, then calculate. This free body diagram is the key to unlock the next question. All right. So I want the magnitude of this force, but I know that this force is being challenged or being opposed by the forces along this plane. All the forces that are acting along the plane have got a direct impact on this force. All right. So let's apply Newton's second law. And another clue that we are told from this question is that the first question says state Newton's second law. So which means basically this calculation is anchoring upon Newton's second law. So let's write Newton's second law. F net is equal to ma. The net force is equal to the product of mass and acceleration. Well, we are told the system accelerates up the incline at 0.25. So the A is 0.25. Right? So when we add all these forces that act parallel to the incline, they are the ones that are causing this system to move like that. So for the 4 kg block, it is these parallel forces that cause the acceleration. So let's add them up. Now before we add them up again, you can clearly see that there are vectors going in opposite directions. It's always easy to make the direction of motion the positive direction. And then all the forces that are opposing become negative forces. And whilst we're at it again, you'll appreciate that when it comes to this force tension, the tension is the same in the sense that the tension that acts on the 4 kg block will be the same tension that acts on the block M. The tension that acts on the 4 kg block is going to be positive tension because it's going in the same direction of motion. The whole system goes up. The tension that acts on M is negative tension. Same magnitude, different directions. Okay, so we're going to have Ft plus Fg parallel plus Ff. All of that is equal to the mass is 4, the acceleration is 0.25. Okay, now do I have Fg parallel? Do I have the frictional force? Now if I look at the question again, they told me that the coefficient of kinetic friction is 0.24. The moment you see that phrase again, coefficient of kinetic friction, they're basically saying you need to calculate the frictional force. Alright? So we now need to do a side calculation for this force and for that force. It's easier to work those forces out and then come and substitute them there than to add everything up. Remember, we say these forces, when we add them here, they must be negative force. So I always say, do the calculation on the side, get the value of the force, come back, make it a negative force. Do the same for these two. These two are all negative forces. Let's start with Fg parallel. Well, we know that Fg parallel is equal to mg times the sine of theta. When it comes to the components of gravity, or the components of a force generally, it's sine and cos. On an inclined plane, it changes a bit. Because on an inclined plane, along the tilted x, the component is sine, and along the tilted y, the component is cos. Normally on a flat surface, we say cos, and then sine. Okay, just be aware of that. Fg perpendicular will be mg cos of theta. All right. So let's work out Fg parallel. We know that Fg parallel is mg times the sine of theta. What is the mass? 4 times 9,8 times the sine of 30. Right? 4. My calculator there. I don't know why I left it there. It's supposed to be with me, naughty calculator. 4 times 9,8 times the sine of 30. 19,6 newtons. It's a negative 19,6. So Ft minus 19.6. That's why I said it's best to first work it out and then determine whether the force is positive or negative when you feed it into your expression. You've got to do that, otherwise you might end up putting a positive force when it's supposed to be negative. Let's work out Fg perpendicular. Why are we going to work out Fg perpendicular? Well, we need to calculate the frictional force. And the frictional force is equal to what? Well, the frictional force is equal to the coefficient of friction times the normal force. So we need the normal force first. So let's get the normal force. What's M4 times 9.8 times the cosine of 30? We're going to get a force. Calculator, 4 times 9.8 times the cos of 30. 33,948. This is not my final answer. I don't round it off. I keep as many decimal places as I can. But generally, I think 3 normally work. Okay? Now, we now need a frictional force. The coefficient was given as 0.24, and this is 33.948. I hope there's not too much information on this board that begins to intimidate, because once the information seems like there's now too much of data, you're going to have a data scaring tactic. It's not a data scaring tactic or a data scaring syndrome where you're now scared of data. Too much information. And I know that young generations are too much information, TMI. Guys, I'm not setting up a TMI. Work with me. 0.24 times 33.948, 8.148. Okay? So where am I going to this? This is 8.148 newtons. Again, make it a negative. Negative 8.148 is equal to 4 times a quarter is 1. Now, to get the value of Ft, group the numbers on the other side, isn't it? All these numbers become plus. So the force of tension, we're going to add all those numbers. 1 plus 19.6 plus 8.148. 1 plus 19.6 plus 8.148. 28.748. 28.748 newtons. 2 decimal places, change that to a 5. 28.75 newtons. So, the force of tension is 28.75 newtons. It's very important to know. That's why I was encouraging you to draw parallel forces. Look how we dealt with the parallel forces. There came a time when we also needed the perpendicular forces to the plane, to the incline. We wanted the normal force. And we said along this incline, these forces balance each other out. So the normal force is equal in magnitude to the component of gravity, this perpendicular component. But they're acting in opposite directions. That's why I wrote this statement here. Fg perpendicular is equal to mg cos theta. Once I knew what Fg perpendicular is, I can also say that that is the magnitude of the normal force, because they are going to be the same. That's how we have a zero resultant along this axis. Sure. Okay. The next question says calculate the value of m. So we want the value of m. And something tells me I'm going to need that value there, 28.75 newtons. Okay? Can I create some space somewhere? 3, 2, 1, shoot. .3.2. We want the value of m. Okay, we want the value of m. Well, how can we calculate the value of m? Well, what if we draw a free body diagram to show all the forces that act on m? The acceleration that the 4 kg block had will be the same that m is, because they accelerate as a system. Okay, so again, tilted Cartesian plane, mimicking the incline. look for perpendicular forces. First force, 50 newtons pulling the whole system up. Next force, the tension, which we said in this case is now negative. This tension is going in the opposite direction of motion, is negative tension. Positive tension, negative tension. Going in downwards again, we have the parallel component of weight, and also going in the same direction, the frictional force. In this case, we can draw the perpendicular forces, but we're not going to need them. Why? Because in the question they said the frictional force is 3 newtons. So we're not going to do that. Frictional force is coefficient times normal force. So we don't need to worry about those forces. Okay? We're going to apply Newton's second law again. F net is equal to ma. The net force that acts is the sum, is equal to the mass times acceleration. One direction has to be positive, one direction has to be negative. 3 negative forces versus 1 positive force. So sometimes it doesn't matter how much negativity you're surrounded by, you can be the only positive force and still accelerate in the direction. Okay, that's physics for another day, the direction that you want. So, the tension force we've got, frictional force we've got, we don't have Fg parallel. So let's calculate Fg parallel. So Fg parallel for this 4 kg is still m times g times the sine of theta. We don't know what the m is, we leave it as m times 9.8 times the sine of 30. The sine of 30 is a half. Half times 9.8 is 4.9. So this is 4.9 m. We're going to make it a negative as well. So let's add them up. So it's 50 newtons plus Ft plus Ff plus Fg parallel is equal to m times 0.25, which is 0.25 m. Next line, the 50 newtons stays, Ft is negative 28.75, frictional force 3, Fg parallel 4.9 m, all of that is 0.25 of m. We can now group, take the, it doesn't matter where the unknown fellow is, it can be on the left hand side, right hand side. I'll move him across, I'll add, becomes a positive, so it's now 4.9 plus 0.25, 5.15. So on this side I have 5.15 of m equals to, subtract all these digits now, 50 minus 28.75 minus 3, 18.25 is equal to 5.15 m. Divide both sides by 5.15, 3.54 kilograms. .54 kgs is equal to m. Okay, so you can use that approach, and you can say the net force is mass times acceleration, and then you get the mass being 3.5 kilograms. When I look at that diagram, I'm seeing another approach. Here we did the individual body approach, but I'm thinking of the system approach. It will eventually come back to this, but yeah, the system approach, okay, Let's do a system approach quickly before we go on to question 2.4. What is the system approach? So we say mass here is M 3,54 kilograms. A system approach simply means instead of looking at individual components of the system, M separately, the 4 kg separately, let's look at the whole system. What is happening at a system level? How does the system move? What are the forces pulling the system up the incline? What are the forces opposing the system? Okay, so there is my system. Combined mass of the system is going to be M plus 4 in terms of the kgs, correct? We don't know what M is. We are going again on an inclined plane. The force that is pulling the system up is the 50 newtons. What are the forces opposing the system? Well, we could look at it this way. The tensions are, remember we said one is positive, one is negative, so effectively they cancel out. A positive tension and a negative tension. So I will not include them on this diagram. I can include the tension in it, they will eventually cancel out. We're going to have friction of M. We're also going to have friction of the 4 kg. Then, supposed to be 4 kg. Then we're going to have the combined FG parallel of this system. Now, I have removed the frictional force of the 4 kg, but I can quickly calculate it. Mu k times Fn. Mu k is 0.24. Fn was mg times cos theta. 8,148. Aha! This is my frictional force. Yeah. Yeah. Alright. Now, I've got all that I need to work out the net force. Remember, this whole system is accelerating at 0.25 meters per square second. The direction of the incline, like that. So, I can still do this and work out M. This normally we call the system approach. Okay, instead of breaking the system into M and 4 kg, combine the two. So let's see how to do. Can we work out the friction of M? We've got friction of the 4. We got. What we don't have is FG parallel of the system. The gravitational force combined pulling this down the incline. So the FG parallel is mg times the sine of theta, which will equal to what? It's m plus 4 times 9.8 times the sine of 30. Sine 30 is half. Half of 9.8 is 4.9. Right? So I'm going to have 4.9 into m plus 4. This becomes 4.9 m plus, what's 4.9 times 4? 19.6. Again, negative. These two fellows, I'm going to have to multiply. This is a negative mg. Now the negative, remember, when you're distributing a negative sign to an expression, it can't be only this term, it has to be that term as well. So, because it's negative, it's going to be negative of 4.9 m plus 19.6. So, negative 4.9 m minus 19.6. Okay, I've got all the ingredients I need. So, F net equals ma. system approach, the whole system combined. 50 minus friction of M was 3, minus friction of the 4 kg was 8.148, minus 4.9 M minus 19.6 is equal to, the combined mass is M plus 4. M plus 4 times 0.25. Okay, let's start grouping the numbers and leave the M fellow. So you're going to have 50 minus 3 minus 8.148 minus 19.6, 19.252. 19.252 minus 4.9 M is equal to 0.25 of M plus 1. Bring the 1 this side. Take the 4.9 that side. So 19.252 divided by 1 becomes 18.252 is equal to 4.9 plus 0.25, 5.15. Divide by 5.15. We've seen that calculation in the previous step. So 18.252 divided by 5.15. We're told about a hypothetical planet red pack with a mass double that of the Earth, radius 3 times that of the Earth. Calculate the weight of an astronaut of mass 75 kgs that lands on the surface of red pack. Okay, so the mass of the Earth is about 5.98 times 10 to the power of 24 kilograms. Radius of the Earth 6.36 times 10 to the power 6 meters. Now, sometimes the examiners will give you this information, but you'll notice that in this question, you could use this information or you might not use this information. We'll show you. I'll explain what I mean. Generally, weight of an object is mass times the gravitational strength where the object is placed, the G of the object. In the case of the Earth, we use 9.8. I know it's a rounded off value, maybe it's more correct to use 9.81 or 9.0 something, but we generally say 9.8, that's fine. Okay? When you move away from the Earth, the G changes, and let's say you land on another planet, we'll use the G of that planet to calculate the weight that you'll experience on that planet. Okay? So there are two ways of calculating the weight. One is to say, go straight for the mg. If I know the mass and the g, I can calculate it. Or I can say, if I know the gravitational force between the Earth and an object placed on the surface of the Earth, it will be the same as the weight. So, this means I've got, so far I can see two ways of doing this. One way, calculate G, or maybe determine G, and then after I've determined G, I use Fg equals mg. The second way might be just to use this idea that gravitational force is the g m e little m over r squared. The third idea that I can use is the idea of proportion, because they're telling me about 3 times the radius is 3 times the mass is. What if I use proportion techniques without even doing the calculation? Okay, let's start with method 1, determine little g, assuming that we got the mass. So if the examiner doesn't give us the mass, then probably number 1 and number 2 are out. That's why it's always handy to have more than one technique. Okay, so let's calculate little g. Little g is gm over r squared, which is 6.67 times 10 to the minus 11. The mass is 3 times. Now for red pack, okay, let's call it G red. Yo, it's your boy G red. Where is G blue? I'm just G red. Okay, so it's 2 times 5.98 times 10 to the power of 24. Radius is 3 times that of the Earth. Squared. Now, I grab the calculator. 6.67 exponent minus 11 times 2 times 5.98 exponent 24 all over 3 times 6.36 exponent 6, all that squared. 2.191. 2.191. There's even a 2 there. 191 meters per square second. From there now I can just say, okay, this times m. See what we're doing? We're basically taking this and multiplying the m, so it's the same. So I now say Fg is mg. 75 was the mass times 2.191. 75 times the answer, alpha answer. I guess I just say the answer. I get 164.35 newtons. Rounded off to 2 decimal places. Alternatively, I can say, using that, okay, let's see where it goes. So using this idea, I'll say the Fg is G m little m r squared. The G doesn't change, universal gravitational constant, times 2, because it's twice the mass of Earth. Guys, that's a 10, looks like a funny 10, all over 3 times 6.36 power 6 squared. I put that on my calculator, should give me that number there, 164.35 newtons, and in both cases it's downwards, because you're on the surface of the Earth, of that planet, so it's downwards. What if I was to use a proportion technique and say, well, instead of calculating little g, I can determine little g. Why? Because the little g has got a relationship with the big M. The little g has got a relationship with the R. So the g is directly proportional to the mass. So we are doubling the mass. So G red is going to be equal to the 9.8, which is the G of the Earth. But now we're doubling the mass, so it's going to be times 2. We're trebling the distance. So, what is the relationship between G and R? Well, we say it's an inverse square law. Remember this one? So, what does that mean? We find the factor that we are changing is 3. Invert the 3 becomes 1 over 3. Square it becomes 1 over 3 squared. Inverse square becomes 1 over 9. So this is now times 1 over 9. So the new G should be equal to that value. 9.8 times 2 times 1 over 9. I get a G of 2,18. Difference to 2,19 here. Maybe if I had used 9,81, not really, because the 9,8 is the rounded off value. So these two values are very much comparable, and I think this will be an acceptable scientific method to get what the G would be, the 2,18. Once you get the G, come back to the formula and then say, oh, so FG becomes 75 times 2,18. $163.5. Slightly different from that, it's fine. Okay, 163.5. In fact, was that the G I got? I got 9.8 times 2 times 1, ABC 9. 1 over 9. 2,177. Maybe if I use 2,177. So let's say 2.177 times 75. Get 163.28. Okay, that's a better answer there. 163.27528. Alternatively, I can also do the same with the weight. I can say Fg is directly proportional to the mass of the planet and inversely proportional distance squared. What will be the mass of the weight of this astronaut on Earth? So on Earth, it will be 75 times 9.8. What's 75 times 9.8? 735. Now, you move to a new planet where the mass is twice the Earth. So the Fg at this planet Red is going to be what? 735 times 2. Why? Because we said the mass is doubled. The gravitational force is directly proportional to m. And then the same thing happens with the distance. It's inversely proportional to the distance squared. So it's going to reduce by 1 over 9. So we're going to have 735 times 2 times 1 over 9. 163.33 newtons. Getting different answers? Okay, but as long as we are seeing that the method is somewhat consistent and correct with science. If the examiners don't give you the mass and they just want you to perform the calculation using a proportion technique, use that. See how close these answers are? They're using the same method. And these other two answers, they're also using another method. Okay, that's it about question 2.4. Remember, guys, we mentioned the idea that you've got to learn the formulas, even if they're given in the formula sheet. Don't fall into the trap and say, I don't need formulas because they're given in the formula sheet. You need them. This kind of skill of performing a calculation needs practice and drilling. When we often see superstars perform, we say, wow, these guys are amazing. They just perform from the blue. But the reality is they train, they practice, they see patterns. To develop a skill, you must be able to see a pattern. It's been nice, it's been fun. I'll meet you on the other side, on the other time when we discuss the other question 3. I think it's projectile motion. We're going to have fun dealing with projectile motion. I hope you had fun dealing with forces, seeing the number of ways you can attempt this. I hope it expands your horizon on how you can approach questions involving force, okay, on an inclined plane. Yeah, that's about it. Kind of feel like I nailed this one, Shot. Yeah. This is good, man. Good. Yeah. All right, I'll see you guys next time. Sure.